Hi, folks. How y'all doing? We're starting section 3.4 today, which is on determinants. Let's go ahead and get started. All right. So, when we're going to review something from last time, we have a 2 by 2 matrix. The determinant of this matrix is the value that we get when we multiply this diagonal, A times B, and then we subtract this diagonal, this product here, B times C. For example, if I want to calculate the determinant of this matrix, the determinant of the matrix is 3 times 6 minus 5 times 4, or 18 minus 20, or negative 2. And a question we might have is, what does the negative 2 mean? Well, this is the answer to that question. Say we have a closed region S in the plane and a transformation whose standard matrix is A. Then the area of the transformed version of S after the transformation is the absolute value of the determinant times the area. That is, the determinant might be positive or negative, but area can't be negative. And so if we accept the negative sign, then the determinant is the magnification or the reduction factor of the linear transformation. So we can look at an example. Let's let S be the unit circle. So this is 1, 1, negative 1, negative 1. And the unit circle goes through all these points. See if I can make that happen. All right. And A is the matrix 3, 0, 0, 2. So what now we know is that the standard vector E1 moves to the position 3, 0. So this is now the transformed version of E1. And the standard vector E2 transforms into 0, 2. So that's 2 units high. This is the transformed version of E2. And so this circle is going to get stretched out into an ellipse. And it should have been a little wider on the other side. Let's try that again. Let's see, negative 3. How about that? A little bit better, maybe. So T is the transformation based on this standard matrix, where the transformed version of E1 is here, the transformed version of E2 is here. Then the transformed version of the circle is this much bigger ellipse. The area of the circle is pi. The determinant of A is 3 times 2 minus 0 times 0, which is 6. That means the area got 6 times bigger, and so the area of this ellipse is 6 times pi. And so we now know the area of this ellipse. Let's try another example. Let's try the area of this ellipse. So again, if we start with the unit circle, S is a unit circle, the area is equal to pi, and these are my standard vectors E1 and E2. The transformed version of E1 is now at the position 2, 2, and the transformed version of E2 is at negative 1, positive 1. And the determinant of this matrix is 2 times 1 minus 2 times negative 1. which is 4. And so the transformation makes the area 4 times bigger. So if we start with an area of 4, this has an area, I'm sorry, starting with an area of pi, this has an area of 4 pi. We'll try a couple more of these examples and then we'll move on to something else. Find the area of this triangle over here. So the triangle on the left, the area is 1/2. And here's E1 and E2. They're two sides of the triangle. These are the transformed versions of E1 and E2. And the matrix for this transformation, E1 transforms into the vector 2, 1, and E2 transforms into the vector -1, 3. The determinant of this matrix is 2 times 3 minus -1 times 1, and that's 7. And so the area becomes 7 times bigger. And so the area over here is 7/2. That's the area of the triangle on the right-hand side. All right, our last area example, and then we'll move on to something else. Let's find the area of this parallelogram. The vertices are 1, 1, 3, 2, 2, 4, and 4, 5. So this time we're going to just start with a square. The area is equal to 1. And here's E1, and here's E2. The transformed versions of E1 and E2 right here. But be careful, we're not starting at the origin. And so the transformed version of E1 doesn't have coordinates 3, 2, it has coordinates 2, 1. And so those are the coordinates of A, the transformed, or the first column of A, E2, 1 unit to the right, 3 units up, and the determinant of this matrix is 2 times 3 minus 1 times 1. That's equal to 5. And so the area is 5 times bigger than we started with. Well, we started with an area of 1, and so this parallelogram has an area of 5. So the determinants are useful in helping us solve area problems in 2 dimensions. In 3 dimensions, they're useful for helping us solve volume problems. And so we would like to be able to find the determinant in a larger dimension, not just in 2 dimensions. And so to do this, we're going to cover 2 definitions. One is the word submatrix. We have a square matrix, then a submatrix of A is what we get when we remove 1 row and 1 column from A. And we use subscripts here to indicate that the row and the column that we have removed. So we've removed row I, we've removed row J. So for example, if this is my matrix A, and I want to find the submatrix 3, 4, then I remove row 3, and I remove column 4, and the remaining entries 1, 3, 0, 2, negative 2, 1, negative 2, 7, negative 2, 9 form the submatrix that we're looking at, A, 3, 4. All right, that's what a submatrix is. A cofactor is taking the determinant of the submatrix, but we're going to multiply it by either a 1 or a -1 according to this rule. We're going to add I plus j together, and if I plus j is even, then we're going to multiply by 1. In other words, there's no change. But if I plus j is odd, we're going to multiply by -1. And this is now the determinant and not the matrix itself. And so we'll use the letter C to indicate a cofactor. Let's try an example. I start with this matrix A, and I want to find the cofactor in the 2, 3 position. That means first I remove row 2, and I remove column 3. I'm taking the submatrix from the 2, 3 position. That leaves with the matrix 1, 3, 3, 5. And that determinant would be 5 minus 9 is -4. But because 2 plus 3 is odd, we also include a factor of -1. And so the cofactor is +4 and not -4. And this gives us one way of calculating the determinant of matrix. We can calculate the determinant of a 3 by 3 matrix using a technique called cofactor expansion. To find the determinant, we will choose any row or any column of that matrix, and we will multiply the entries in that row by the cofactors in that row or in that column, and then add up the products we found. We'll work through a couple of examples, and then we will show another way of finding a determinant besides using cofactors. So in this example, we want to find cofactor expansion to compute this determinant. So in our first step, we choose a row or a column. And I'm going to choose the top row because it has a 0 in it, and 0 will be easy to multiply. So I'm choosing the top row, but I didn't have to. I could have chosen any row or any column. The determinant of A is the numbers in the row. So 1 times the cofactor in that position, which is the 1, 1 position, plus 3 times the cofactor in this position, which is 1, 2, plus 0 times the cofactor in the 1, 3 position. So in the 1, 1 position, if we were to remove the first row and the first column, the numbers that we would have left would be 2, -1, 4, 1. Then we get 3 times the determinant. In the 1, 2 position, we would eliminate the first row and the second column. And now we're looking at 2, -1, 1, 1. But 1 plus 2 is odd. And so instead of multiplying by 3, we're also going to put a negative factor in here. So this is going to be -3. And then we're going to get 0 times something, but I don't care what that is because 0 times anything is 0. And so this is going to be 2 minus a -4 is 6. And then this is going to be -3 times 2 minus a -1 is 3. And so this is going to be 6 plus -9. And my final answer is -3. That's the determinant of this matrix. All right. Some books use vertical bars, not square brackets around the matrix. And so if we just see what looks like the absolute value of a matrix, it means the determinant. It is these two notations mean the same thing. And the answer, like we just saw, is -3. We'll do one more example and then we'll move on. We're going to compute this determinant using two different cofactor expansions. I want to show you that you get the same answer both ways. So in the first expansion, we're going to try using the bottom row. If we use the bottom row, the determinant of A is -1 times the cofactor in this position, which is 3, 1, plus 0 times the cofactor in the 3, 2 position, plus 0 times the cofactor in the 3, 3 position. But I don't care about those because they're getting multiplied by 0. And so this is going to be -1 times the determinant in the 3, 1 position. We're left with -1, 0, 3, -2. And that's -1 times 2 minus 0, which is 2. And that gives us a final answer of -2. Oh, I didn't mean to do that. That actually erased everything, not just the annotations. Okay, well, sorry about that. Let's try this again. Instead of using the bottom row, we're going to use the right column. And now the determinant is 0 times the cofactor in position 1, 3, minus 2 times the cofactor in position 2, 3, plus 0 times the cofactor in position 3, 3. And again, 0 times anything I don't care about. And so this is going to be -2 times the determinant of this matrix. 2, -1, 2, -1 in the top row, -1, 0 in the bottom row. But 2 plus 3 is odd. And so we're going to change the sign and make this a +2. This determinant is 0 minus 1, which is -1. 2 times -1 is once again -2. We get the same answer even though we did a different cofactor expansion. We always get the same answer. All right, let's move on. If a square matrix is in echelon form, then we have a shortcut for finding its determinant. For example, right here, if I want to find the determinant of this matrix using cofactor expansion, I'm going to expand down the top column, first column. The determinant of A is going to be 3 times the cofactor in the 1, 1 position, plus a bunch of zeros. And in the 1, 1 position, cross out the first row in the first column. Now we're looking at the determinant of 2, -35, 0, and 5. But that determinant is just 2 times 5 because the other diagonal has a 0 on it. And so the answer is that we just get 3 and 2 and 5, and we multiply those together, and we get 30. That's a nice pattern, is that the answer just turned out to be the product if we had just multiplied down the diagonal. And that works in general. If the matrix is in echelon form, A is in echelon form, we can multiply the diagonal and that'll give us the correct answer. So 3 times -2 times +2 times 5 times -3, and that's, let's see, 18 times 10 is 180. So that works if the matrix is already in echelon form. If the matrix is not in echelon form, we can use row reduction to convert a matrix in echelon form, but row reduction changes the determinant. And so we have to keep track of these changes as we go. So let's look at the legal row reduction steps, see what happens, and then we're going to do some examples where we try this. So first step, we're allowed to switch two rows of a matrix when we row reduce. But when we do that, that changes the sign of the determinant. In the original matrix, this is 12 minus 10. But if I switch the two rows, so we switch row 1 and row 2, now my determinant is 10 minus 12, and the sign changed. And so switching two rows of a matrix changes the sign of the determinant. We're allowed to scale a row, multiply or divide a row by a constant, but it changes the determinant by the same amount. Here's an example of that. I have the matrix 4, 8, 1, 5. My determinant is 20 minus 8, and that's equal to 12. But if I do the row reduction step, row 1 divided by 4, so that the 4, 8 becomes a 1, 2, now my determinant is 5 minus 2, because I got rid of a factor of 4, and my answer is now 3. The determinant also went down by a factor of 4. So we can scale a row, but that changes the determinant by the same amount. Here's the third rule. We can replace a row with a linear combination. Now this is a little tricky, and the book describes this a little differently. But let's work through this. Adding a multiple of a row to another row changes the determinant by the coefficient of the row that was changed. Let me show an example. If we start with the matrix 1, 2, 4, 7, that determinant is 7 minus 8, which is negative 1. And I'd like to eliminate that 4 and put the matrix into echelon form. So if we do row 2 minus 4 row 1, that's 4 minus 4 is 0, 7 minus 8 is negative 1. Then we changed row 2. Row 2 was the row that changed, but the coefficient in row 2 is a 1, and multiplying by 1 does not change the answer. And so this determinant is still negative 1. Negative 1 before is negative 1 afterwards. Negative 1 minus 0 in this case. But here's a different example. Suppose we have 4, 5, 2, 3. That determinant is 12 minus 10, which is 2. And I want to erase this 2. So we're going to do the row reduction step. 2 times row 2 minus row 1. 2 times 2 is 4. 4 minus 4 is 0. 2 times 3 is 6. 6 minus 5 is 1. But now the determinant is 4 minus 0, which is 4. The determinant went up by a factor of 2. And the reason for that is that row 2 is the row that changed, but we doubled row 2 in the process. And so the coefficient of the linear combination here in front of the 2 also indicates how the determinant has changed. Okay? So let's review what we just saw. What happens to the determinant if I multiply row 3 by negative 4? then the determinant also gets multiplied by -4. What happens if I use this row reduction step to change row 3? Answer is there is no change, because the coefficient in front of row 3 is a 1, and multiplying by 1 doesn't change anything. What happens if we switch row 2 and row 4? Then the determinant changes signs. Anytime you switch 2 rows, the determinant changes signs. And the last one, what happens if we use this linear combination to change row 1? Well, the coefficient in front of row 1 is a -1, and so once again the determinant changes signs, because we'll have to multiply it by -1. The next example is somewhat long, but it's going to use all of this information here. We're going to try to compute the determinant of this matrix here. So the determinant of this matrix, we're going to get rid of this 1 by taking row 3 minus row 1. When we do that, 1 minus 1 will be 0, 5 minus 1 will be 4, 6 minus 3 will be 3, 8 minus 4 will be 4, and 5 minus 2 will be 3. And I'll fill in the rest of the entries here. Give me a second. Now, what effect does this have on the matrix? On the determinant? It has no effect, because we changed row 3, and the coefficient in front of row 3 is a 1, and so this step has no change. So we don't have to do anything yet, because we did not change the determinant. But I want to look now. Here are my leading entries. My leading entries in rows 2 and 3 are out of order, and so I'd like to switch row 2 and row 3. So now we're going to switch row 2 and row 3. So that gives me 1, 1, 3, 4, 2, 0, 4, 3, 4, 3, 0, 0, 2, 3, 5, 0, 0, 0, 3, 4, 0, 0, 3, 6, 1. But this effect changes the sign of the determinant, and so I'm going to put a negative sign out there to change it back. Because we did a row reduction that changes the answer, we have to undo that change also. And so now we have a negative sign out here. So now these are my leading entries, 1, 4, 2, 3, and 3. I want to get rid of this 3. So I'm going to do this linear combination, 2 times row 5 minus 3 times row 3. And let's see what happens when we do that. Give myself some space here. So the top row stays the same. All right. 2 times 3 is 6. 3 times 2 is 6. 6 minus 6 cancels and goes away. 2 times 6 is 12. 3 times 3 is 9. 12 minus 9 is 3. 2 times 1 is 2. 3 times 5 is 15. 2 minus 15 is a negative 13. What effect did this step have on the determinant? Since I was changing row 5, the 2 caused the determinant to double. And so now I have to multiply by 1/2 to cancel out the doubling. So I now have a negative sign and I have a 1/2 over here. But we're almost done with echelon form. We just need to get rid of this 3. So we're going to take row 4 and row 5 and we'll subtract them. I'll say row 5 minus row 4. Three minus 3 is 0. Negative 13 minus 4 is negative 17. What effect did this have on the determinant? Since we were changing row 5, there is no change, but we still have a negative 1/2 from previous steps. This is now in echelon form. And so the determinant we get by multiplying down the diagonal, but we also have a negative 1/2 out in front. And so the determinant of this matrix, the final answer, is negative 1/2 times 1 times 4 times 2 times 3 times negative 17. That's 12 times 17, which is 204. All right. Sounds good. We'll move on next time and look at another topic. Thank you for coming. I'll see you around.